Explain the graph of f prime, which is given, and its corresponding f. Find any critical numbers, the location, which are the x-coordinates of any extreme values and inflection points. The extreme values are the local minimum and local maximum. To determine this, we should construct the sign chart to obtain the information about f prime. The graph of f prime is given. We see that f prime is above the x-axis between 1 to 3. From x equals 1 to x equals 3, f prime is positive. F prime is negative from 0 to 1, and then from 3 to 4. We see that the function f is decreasing from 0 to 1, increasing from 1 to 3, and then decreasing again from 3 to 4. That is the graph of f. We then construct the sign chart for f double prime as well. For f double prime, we see that f prime is increasing from 0 to 2. It is climbing up on the interval 0 to 2, so f double prime is positive. F prime is decreasing from 2 to 4, so f double prime is negative from 2 to 4. From the sign chart for f double prime, we see that the graph of f has an inflection point at x equal 2 because f double prime changes its sign at x equal 2. Also, the graph of f is concave up from 0 to 2 and concave down from 2 to 4. To summarize this, for the graph of f, we see that it has a local minimum at x equals 1 because f prime changes its sign from negative to positive at x equals 1, meaning the graph of f is decreasing and then increasing at x equals 1, local minimum. Similarly, it has a local maximum at x equals 3 because f prime changes its sign from positive to negative, increasing and then decreasing at x equals 3, local maximum. We don't know what the y coordinate is because we don't have the information about f. From the sign chart for f double prime, we see that f has an inflection point at x equals 2 because f double prime changes its sign at x equals 2. Also, since f prime is 0 at x equals 1 and x equals 3, we have two critical numbers, and they are x equals 1 and x equals 3. To sketch the graph of f, we use the sign chart of f prime and f double prime to determine the shape of the graph. From 0 to 1, the graph of f is decreasing because f prime is negative, and concave up because f double prime is positive as long as it is decreasing and concave up. From 1 to 2, the graph of f is increasing because f prime is positive and concave up because f double prime is positive, increasing and concave up. From 2 to 3, the graph of f is increasing and concave down, increasing, concave down. From 3 to 4, the graph of f is decreasing and concave down. The shape is decreasing and concave down. We are not given the initial value, so we can start at any height. Why don't we start at x equals 0, y equals 0. The graph is decreasing and concave up from 0 to 1, increasing and concave up from 1 to 2, increasing and concave down from 2 to 3, and then decreasing and concave down from 3 to 4. This graph is not unique because we can shape it up or down. If we start at x equals 0, y equals 1, we would have a similar shape from 0 to 1, decreasing and concave up, 1 to 2, increasing and concave up, and so on. The graph of f prime has a corner at x equal 2. That means f double prime does not exist at x equal 2. We see that x equal 2 is in the domain though, so we have an inflection point for the graph of f. Also, because of the symmetry of the graph of f prime, we should draw the graph of f that is symmetric about x equal 2 as well. There is a good chance that this is a piecewise function. We can probably guess what it is. F prime of x, it is, the first part is 2x minus 2. The slope is rise 4 over 2. So the slope is 2 and the y-intercept is negative 2. For x between 0 and 2. An antiderivative for the first p, if we were to guess it, it would be x squared minus 2x. And again, it can be shifting up or down with a constant. This is the antiderivative on the interval 0 to 2. From 2 to 4, the formula for f prime is negative 2x plus 6, because when x equals 2, y equals 2. Negative 2 times 2 plus 6 is 2. And when x equals 3, negative 2 times 3 is negative 6 plus 6 is 0. It is a linear equation. This is for x between 2 and 4. An antiderivative for negative 2x plus 6 would be negative x squared plus 6x. And again, it might be up by a constant. We would call it C2. This formula is only for an antiderivative from 2 to 4. If we're going to make a guess, we should always check this. The derivative of x squared is 2x. The derivative of negative 2x is negative 2. And the derivative of a constant C1 is 0. Similarly, the derivative of negative x squared plus 6x plus C2 is negative 2x plus 6. This might look like a version of the graph of negative sine of omega x. We will need to change the period. Although we won't be able to use the function sine in this case because we know that the second derivative does not exist at x equals 2, and that is the reason why we use the piecewise function instead.